Okay guys, let's talk about Ramanujan. 1 plus 2 plus 3 plus dot 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 equals negative 1/12. Now, Ramanujan wrote that, so he must be an idiot, right? From what I hear from other people, this is sort of what... In fact, he was actually worried about showing his axiom basis to other people, and he wrote a letter to Hardy actually explaining that. Now, he didn't put an R, so he didn't say, oh no, it's the Ramanujan sum. So he didn't put an R there. He said they were equal. But the funny thing is some people will say, no, that's infinity. Okay, then that's not a function. The definition of summation is, let's see if we can define it inductively. You have a zero, or you have the successor of some integer, okay? And that gives you your possible integers, right? So you have 0, you have successor of 0. Summation just shifts all the successors. So the definition of integer plus integer, you could redefine that as saying, well, if it's 0, so for a plus b, if a is 0, then it's b. But if a is an integer that is made up of a successor of something, say c, then it would be c plus successor b. Now you can say, oh, there's so many different definitions you could pick for summation. Yeah, but this one is only going to evaluate if you have a finite number of operations. But what does the dot 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 mean? Does it mean you have an infinite number of operations? Or can you use another variable to reason about it in an abstract way? So, if we're going to define functions, right, or operators about integers, and we want to make expressions, well, our expressions have to be finitely linked because we can't write an infinitely long expression. We also have to give back at least something that's a real, right, or maybe a rational, or something that's... Infinity just means non-finite if you actually break apart what the semantics are. So, problem with these people is they've fallen for a lie, and I'm going to show you the rationality behind that lie. I want you to look up the definition of convergence and tell me if it looks complicated or simple. It's pretty complicated. It's talking about an epsilon. You have an epsilon, you have a delta, and then you talk about the distance, the size. You're talking about their absolute values, and you're going to tell me that, oh, when you have an infinite sum, it has to converge to get you a number, but if it diverges, we put an infinity symbol. You guys ever thought about how functions in a program work? You assign a value for everything. When you're defining a type, you have to explain for every case. You can't pick some cases and throw out others. So there's a reason why -12 will show up in mathematics and in physics, because that number is significant to that sum. And when you pick your right axioms to construct what the definition of an infinite sum is, you'll realize that it's actually the most intuitive, and it follows Occam's razor. And Occam's razor tells you how to pick axioms, because you can pick different axioms. Like I can pick how I want to handle dividing by 0 in my programming language. I don't have to just do it one way or another. I can pick something. Or if you take, say, if you want to define 0 to the 0 power, if you look at approaching those numbers from different directions, you'll see that there's a vertical spike. It can be 1, it can be 0, it can be somewhere in between, depending on how you approach the thing. So let's talk about the approaching. And I don't want to get into defining limits and everything like that. I just want to talk about, let's talk about finite sums. Because we're going to choose for some random reason to define convergence and then define our infinite sum based on convergence definitions, which you have an elegant, beautiful, simple equation, and now you're going to define it with a convoluted, extremely complicated, artificial set of propositions. Then we're going to have, let's say, a whole bunch of numbers here. So what do we get? We get some big number, okay. So you start adding up a bunch of numbers, and you get a big number over here. But you're always going to have the dot, dot, dot in a finite sum. And if the finite sum starts from 1 and goes up, then wherever you stop in the finite sum, and this is arbitrary, so it's for all possible finite sums, which there's infinitely many, but it's still true for all of them, you're always going to have a number that's finite, and over here you're going to either have what you consider to be an infinite number of adds, or an operator that's, if you were to keep summing, you would be adding numbers that are bigger than all of the numbers that you've had previously. So what they're saying when they try to tell you, oh, this gets bigger, so therefore the answer is infinite. No, because this is added to something, and this is negligible compared to that. And also the number of operators that you've done is negligible. So do another thing for your homework, other than looking up the definition of convergence, and tell me how you do the algebra until you get negative 1/12 on the right-hand side. And tell me which one sounds more complicated, first of all, and which one depends on less axioms. So we're going to decide for our definition of infinite sum to use Occam's razor to give us axioms that give us the simplest explanation. So least complicated axioms is a positive. Less number of axioms is a positive. And on top of that, a closed function. So a function where you could plug things in that are your numbers, like maybe reals or integers, and it gives you back something of that type. So maybe it gives us a negative rational, but that's still a finite number. So go ahead and take all that into account, and then look at any physics studies that have been related to infinite sums and tell me which numbers have been more useful for patterns that follow a convergence equation. So patterns in physics that when you parameterize one side, 1 plus 1/2 plus 1/4, okay, that gives you 2, but that converges, okay? So tell me, for something that when you plug in numbers and it converges, tell me what happens when you plug in numbers that diverge, but then you use the Ramanujan summation. And tell me what happens to the system. Does it follow the Ramanujan sum? Or does it do something completely different where infinity says, oh yeah, no, this is different, a different case entirely? And tell me which one it follows more. So far, all the evidence that I've found, all the information that I've seen, it always gives me a Ramanujan sum as your preferred set of axioms. So people won't like it because they feel like they have some kind of argument. Infinity doesn't wrap around. Okay, well, what happens when you take a sphere and you project a light from the top of the sphere onto a plane, and part of that sphere has a transparent square? You rotate the square up around to the top, what happens? The side of one of the squares goes out, stretches, and now you have the same line segment that goes off into infinity that direction and goes off into infinity in the other direction. Even though you just transformed an object that's projecting that in a higher dimension. So if your argument is just, well, intuitively, infinity can't wrap around because somebody said that before, that's also false. So somebody find me an actual argument that holds up that tells me that the definition of the simplest default form of an infinite sum would not get you negative 112. You don't have to call it Ramanujan summation. You should just be able to call it an infinite sum without appending any other caveat, no asterisk. Okay? It's just this. This is an infinite sum. Somebody marks it as correct because according to the most basic axioms chosen by the best strategies, this is a correct equation. Somebody prove me wrong. Show me how you can use simpler axioms. So obviously not convergence versus divergence tests and all that stuff, to show me that this has to be a different value than that. And then we can talk about it. Then we can argue. But you have this, by the way, the smartest mathematician in the world, Ramanujan. You might say, oh, was he really the smartest? Okay, well, let's just put it this way. Hilbert was considered an 80, right, by Hardy, who kicked butt in all of whatever university Hardy was in. He would compete. Was it in the UK? Was it in England? I don't even remember all the details. But Hardy, he labeled himself a 20. So he was already a well-known or a well-established mathematician. He said he was on a 20 of a scale of 0 to 100 or 1 to 100. He said Hilbert would have been at an 80. And then he said that Ramanujan would have been at a 100. And we also have other things to show that Ramanujan, this is the simplest of what Ramanujan has done, but Ramanujan would come up with sophisticated approximations for pi that weren't even exact. He would come up with things that weren't even exact, but somehow didn't have the proofs for them, and yet they are extreme. It's almost difficult to understand how computationally someone could have come up with the formulas that converge so quickly towards the approximation values they came up with. So basically, the best or one of the best mathematicians of all time in history wrote it exactly like this, but he didn't want to be showing everybody what he was talking about because he himself even understood that some people might want to take him and put him in some sort of, you know, mental health facility because of it. So, respects to Ramanujan. Sadly, he had passed away while he was still young, but yeah. Someone show me a shorter proof, but you have to include all the axioms. And I didn't put the proof for this one here, but it's only a few algebraic steps. But remember, we have to define all our axioms here, so you can't just say, well, assume convergence. Like, you can't say things in English. Like, if you're going to use convergence, you have to write it all out and prove it and everything. Include all that because that's your axiom basis here. So, but this, the number of steps involved with that, involving basic algebra rules, subtracting from both sides, multiplying by both sides, things like that. You only have a couple steps for that. So someone come up with a better proof, or someone come up with an argument for a better axiomatic basis, and then we'll argue about it. But as far as I understand, if you just say the infinite sum, then you shouldn't put infinity. You should put, for this equation, you should put -1/12, because that would be the most intuitive and most natural set of axioms to use. So if your math teacher or professor or somebody disagrees, then just ask them, well, what is your axiomatic basis? Show me the proof. And if they start bringing up convergence or pointing to a textbook that uses convergence, well, then you know that you have something that's going to be shorter. And you know that they're using a traditional or a academic created definition instead of the most intuitive or the most straightforward or the most aligned to Occam's razor definition. Anyway, let me know. I just made this video because I saw somebody had made a video about it, and then they put an R above the equal sign, and then they say, well, we know that it's actually infinity. And I'm like, no, because actually Ramanujan summation should be just the standard definition of infinite sums. So we should redefine them. But I'm making this video because maybe somebody disagrees. And I just want to know why they disagree, because I think that Ramanujan summation it should be considered the primary one. If you want to define convergence and divergence, that's fine. I'm not against it. I just don't think that it should be considered the primary definition of an infinite sum. It still can be used. You still can play around with it and do math, and you're free. But I would call that a secondary definition, an alternate form, an alternate definition of an infinite sum. So let me know what you guys think. See you later.